Right, so welcome everyone to our current lecture on algorithms. Today we will talk about the branch and bound technique for solving certain type of problems. And it is not going to be maybe a completely new technique, but it's going to be a combination of some previous techniques such as divide and conquer approach, and some other approach such as greedy approach, perhaps a little bit of greed. But first let's talk about, of course, the midterm. I still have to grade the extra makeup midterms, the two missing ones. But the rest, again, I think you are pretty satisfied with grades. Are you okay? I really talked about those who didn't hear me before, right? You on the midterm was not too hard, I guess, right? That's what I get. So I should make it harder next time, right?
No, it was fine.
Excuse me?
It was fine.
It was fun. It was fun. Okay, good. Okay, good. Just the right size, right? Like Goldilocks, right? So, all right. So. Okay, so let's talk about this branch and bound technique. Again, as usual, I will do also some coding probably in the second part of the lecture, but let's talk about some theory, at least the basic concepts. So, again, it's basically a way of dividing the problem in larger subsets of the problem, right? So, because of course you have some large problem, you don't even know where to begin, right? Again, so you divide in smaller subproblems until you know what to do, right? That's the basic idea in general, right? Again, divide and conquer sometimes used in very specific sense. Here we're just kind of maybe using it in more general sense. I hope I am recording this, right? So you divide it, right? So you divide, you have some the sea of possible solutions. And you try to find the best solution, right? So you divide into smaller subsets, and then you make some estimates or bounds for these solutions. That's the core idea. So this means you need a cheat. You need a cheat, basically. You need a sort of like a cheat for estimation, right? So of course, because if the estimation involves doing the same thing as solving, then you really have not gained anything. So what's the idea, right? Idea gives you bound, so you're conquering this. It's called also fathoming in this particular domain, right? So basically, what you usually do, you relax. And relaxing also has a specific meaning. What does it mean, relax, in terms of solving algorithms? You relax some particular condition of the problem. Meaning you set aside some specific constraint, right? And you solve an easier problem, right? But what does it give you? What does solving an easier problem give you? It gives you a bound, right? Even if the problem is really easy, we cannot do better than this, basically, right? You create a set of bounds, and then you can use that to make estimates. Okay, is this branch of the problem worth solving, actually? Or maybe it's not worth solving at all, we can just throw it out immediately. So let's look at this example. Again, we already know our linear programming example here in this particular case. But the branch and bound could be used in some other problems too, right? So here, we have a branch and bound problem, right? And we have what kind of constraints do we have? We have to maximize this function, x5, x1 plus 8x2, right? x1 is here, x2 is there. Unfortunately, it's not the things that are as easy, not as usual, because x1 and x2, they both have to be integers, right? And so this means this possible solution space might not lie on the edge or the vertex, right? It might not be on a vertex, right? It might not be even on an edge. It might be somewhere inside, right? So somewhere possibly here, right? And it looks like the actual solution. It shows you the actual solution. It looks like here, but that is the actual non-integer solution, right? This is what we would solve previous lecture, right? We type in linear programming, right? And we can solve the equation, and basically that's what we will get. Unfortunately, that's not integers. None of them are integers, right? However, it will give us some ways of working with the integer solution, right? Because we know, okay, yeah, maybe it's one of these integers, but again, remember, you're not guaranteed that these could be integers, right? It could be one of these integers, maybe this one, right? Could be. Obviously, it's not going to be any of these, right? It shouldn't be any of these inside, right? But it could be one of those, and that is actually, in general case, it becomes what you call computationally infeasible, right? We'll talk about computational complexity in some other lecture, but basically it's not possible to do it in a deterministic polynomial time, basically, in general case, which means it's basically not solvable. You cannot find the optimal solution. However, it turns out most of these problems can be, you can get pretty good approximation usually. So let's see what we can do here. This is the easy one. Of course, here we could solve this even with the brute force, right? We have how many possible solutions? You have 1, 2, you have 6 and 5, so about, well, 30 solutions, but of course you can throw away, some of those are completely not allowed, right? So you just go through 30 or 42 solutions. You have 7 and 6, right? So 42 possible solutions on basically, and that's brute force here. If you had, if you had a problem like this, you have to solve it. Obviously, with only 42 possible solutions, actual computation and brute force would be completely fine, right? So again, even if you have 100, two-dimensional, only 2 variables, and maybe 100 times 100, no problem, right? That's only 10,000 things to look through, possible, solutions to look through, right? It's only when you have like maybe 5 variables, 5, on which each have 100 values, 100 to the 5th, that's pretty big, right? And so on, right? That's what, that is what 10 zeros, right? 10 zeros. That's that's 10 billion, right? No, yeah, I guess. All right, but, so integers, so this is what makes it seems like a seemingly easier problem actually becomes harder, because obviously integer solutions, that means, right, that you have less, right? You have actually finite number of solutions, at least it's finite. Previously with the regular non-integer, floating point solutions, you had possibly infinite solutions, but it turned out that is easier. Okay, so that's a big idea. I mentioned this already. So basically, if you can relax it, right? So relaxation means, like not sleeping, but this means actually relaxing some constraint. And here we are relaxing this this fact that it's integer, right? So that's the optimum. So basically, this is the best we can do. Basically, 41.25, right? This is our upper bound, right? No matter how well we do, right? No matter what kind of integers we find, they're not going to be this, because this is how we found this. So basically start by solving this integer problem by solving the regular floating point problem, right? So you try to maximize in this case, right? So upper bound. Okay, so far so good, right?
Yes.
Okay. All right, so, and then there's branching step. So we partition the problem in possible solutions basically, right? So we basically we branch on some particular variable, right? It could be x2, x1, x5, right? They only have 2 variables here, right? So we observe, right, that if you have this part here, right, x2, right, x2 could be what value? You could take a value of 3 or less, or 4 or more, right? This part here, it has to be 4 or 3, right? It cannot be, 3.75, right? So we have to look, we can branch, we can divide, branching means dividing, right? We divide the solution space in these 2 areas, right? So that's the idea, right? So basically we create 2 subproblems, right? Subproblem 1, where formally x2 is less or equal to 3, or formally x2 over more than 4, right? And again, we know that the optimal solution is not here, right? Obviously, right? So graphically, we've done this basically, right? We just created these 2 subproblem spaces basically. So we need to find a solution. We solve it, right? 2 solutions, right? So, and what do we find, right? I remember we are solving this linearly, right? It's a regular floating point solution, right? Which has good algorithms like simplex algorithms, things like that, right? So what do we find? Well, we find that this 3, right, gives you value 39, right? This particular space. Here, well, we end up with solution 1.84 with the value 41, right? So, are we done yet? What do you think? Are we done? Not yet, because we still have a lecture to go through, like half an hour, right? No, that's a good algorithm to think, right? So, yeah, so what's the problem? What is the problem? What do you think? What's the problem here?
Well, the second sub problem has value.
Yeah.
But at the same time, it has floating point numbers, so
Yeah.
we should likely check
Yeah. So, but what is the good news?
that we have found one solution.
Yeah, we have 39, which is again, I mean, if you had some sort of like maybe you say, okay, you have like up to 3 points, you know, it's 41.2, but it was 40, how much was it? 41 to 25, and if you are allowed to, okay, you know, have like some leeway, like some, you know, some delta, maybe, you know, 3 points, then you could go home already. Say, okay, I'm good enough. I don't want to spend any more time on this problem, right? But of course, yes, we still should check. We're not done because we could have possibly better. So this is already sort of like a lower bound, right? Right? It doesn't. So this means that it does not. But this is an important point. It does not make sense to check any solution spaces where optimal values are under 39, right? Because we'll be able to just discard right now if we keep branching, right? And we end up with place where the optimal value is less than 39, we ignore those. We can just say, okay, ignore, you know, set aside, right? So we can cut them early, right? So this is a good point. So we have lower bound is 39. Well, upper bound, well, this is not really nothing, basically, right? So this is not, doesn't give us much, but it means we have to explore these spaces still. Okay, now, so here, well, the problem is here, this is already, it's an integer, like this is a problem here, right? So we are not going to explore this anymore. This is it, right? We can't do any better here, right? Because this already space has the integer value. So that's also good for us. So we have a solution 3. Again, next week we start with graphs and trees, but again, of course, 3 here, right? We have 2 branches, x less or equal than 3, 3, right? And this is 1.44, right? So we can dismiss. So we can dismiss here. Basically, this is already we have solution, right? So lower bound is 39. Upper bound, well, 41 or is it 41.25 technically, right? Integer. Does this have to be integer? Actually, we could think about. Well, I guess arise because the formula gives you integers, but we don't really know if this is going to be integer, right? Well, here I guess actually this is upper bound, I guess, right? Because this is right. So this is upper bound. This is lower bound. This is upper bound. So we have to check this part here. We still have to branch here. So what can we branch now? We only have this left. Maybe I'll draw a nice little. Where's my drawing? Where's my drawer? Draw. Which was it? I forget now. Design? No. Insert. Where's my? Usually, what do I use for drawing? Design? No. Insert. Comment. Oh. Here. No. I guess no. Not. I just want to do some freeform drawing. No. Oh yeah, we can do this. Okay. Curve. All right. Oops. Okay, that worked great. Right. And now, of course, I have to see about. We don't want this. We want no outline. No, we want outline. But we don't want theme colors.
Shape fill.
Shape fill? Yeah, none. No fill. Yep. But then we don't have anything.
Shape outline.
And then show to outline will do this green thing. Oh yeah, perfect. Super. All right. So you guys see so this is what we need to check this one basically, right? So what can we branch on, right? Well, it says 1.8, right? So we are going to branch on x1 basically, right? This value. So we're going to divide in this part on, well, here, right? We're going to divide here, but, well, you can only see there's nothing here, but we still have to check, right? Graphically, we only see that we only have to check this part here, right? So in this particular example, our branches are actually really shallow, right? I mean, we can immediately dismiss some of them, right? So that's really nice for learning example. But of course, in real life, it will not be so simple, right? So basically, yeah. So this is what we are doing, right? So we have this sub-problem 3 and sub-problem 4, right? And here you can say infeasible, right? Because, well, we just don't have it, right? We don't have it doesn't meet the other constraints, right? So now what we do is we find a new problem, we find a new value that is actually 1 and 4.44, right? With value 40, 55, right? So this here. So we just got rid of this part. However, we still need to do something here, right? Because we got a solution, but the problem, and it's also pretty nice, it's more than 39, right? 40.55 is more than 39. Unfortunately, what the problem is,
We still have to check again.
yeah, because it's again, now we have this integer, but unfortunately now this is not an integer, right? It's a float again. So what do? So we're gonna branch again, and we're gonna branch on this part again. So we're sort of moving away, right? We're moving like, so we're cutting pieces. It's like, I don't know, I guess analogy would be how I cut my bread sometimes, or cheese sometimes, like, or something, or cake, right? My wife hates it. I cut half, and then I cut another half, another half, right? You know, just to annoy her, right? So, so it's smaller pieces, right? So, but yeah, so now, so we're gonna branch on this one here, right? So branch here, right? I don't know if you can actually see here, right? So, and yeah, so we got here. So this is our solution 3, yeah. So we cut this is fatum or dismissed, you know, infeasible. So we only still have to check this. So we are gonna branch here, right? 2 more branches, and again it's gonna be what branch on x2, right? And what's interesting is that we are branching again on the same value, right? So it's completely possible in this branch and bone approach that we keep branching on, well, we're going back and forth because we only have 2 variables, right? But we could branch again on a value we already branched before. That's normal, right? Branching variable might recur, right? So in this case, it is x2, right? Again, important point. Now, so we're almost done. We're almost done. And we'll get to here, right? So basically, I only have 2 points to check: 4, 0, 5, and well, 1, 4, and well, this area, 2 areas, right? Yeah. So we have 2 values, right? So this problem here, right? Oh no, this one here, 1, 4, right? This has 2 points, 2 possible solutions, right? 0, 4, 1, 4, and again, we get a linear solution with integer values, but the value is 37. 1, 4 gives you 37. So ironically, well, the optimal solution comes out to be 0, 5 with value 40. In this case, it is here, right? Up here, and that is 40. And 40 is more than 39, right? Remember we had 3 solution. So obviously, again, simple math. So that looks like we cannot, there's nothing to branch on anymore, right? So 0, 5 looks like the solution. Again, if you look at it graphically, the 3, this is integer, right? Infeasible, right? This is our original, right? Upper bound. So we went through this and we end up here, right? And again, hopefully, again, it seems obvious now if you look at it, right? That there's you cannot do better, right? There's nothing else to explore. Well, again, yeah, you can see, okay, you could say, okay, you can branch here, right? You have 2 possible solutions, you know, but obviously it's 37, so there's nothing to explore because we already know there's 39, right, is the upper limit. So there's no point. This is a dead branch, right? Even if there's possible more solutions to explore here, right? But that's it. So what have we done in essence? If you think about it, go back, right? So basically, instead of exploring all these extra points, by using this linear approach, right, we are able to only move along, only explore a few points, basically, right? So pretty cool technique. The only thing is, I think it's been proven that in some extreme case, it's not going to do better than just regular, brute force. Actually, like it can degenerate to something, right? So, but usually it works extremely well, right? So, and again, it does not have to be. Linear programming, right? So does this make sense?
Yes.
More or less. Okay, great. Right. So, all right. So now we have an example. We could try to solve this one, right? So we have 0, 1. Okay. Well, this one is really easy, of course, right? Because why is this so easy? Because we only have, how many solutions do we have if you think about this here, right? Well, it's kind of like this constraint, right? Look at this constraint. It means that x1, x2 can be only what values?
Well, there will likely have to be 0 and 1.
0 or 1. So how many possible, if you have brute force, how many solutions do we have check?
1.
No. It says x1 and x2 is in middle, right? This is not strong, this is weak equality, right? Less or equal, more or equal, less than equal, right? So x1 and x2 could be 0 or 1, right? We have two variables, each could take two possible values, so what's the brute force? How many brute force solutions do we have to check? How many? Not just one. So x1, maybe this is not, so x1 could be 0 or 1. x2 also could be 0 or 1, right? So how many solutions? How many do I have to check? If I had brute force, I don't know anything about branch and bound or anything. Well, what can I do? How could I solve this with brute force? When I say brute force, I just want to plug in the values, right? The legal values. So how many legal, combinations I have?
4.
Yeah, 4, of course, because we have two ways. Each has 2, right? So only 2 variables, so 2 to the 2, right? Which is 4, right? If you had 3 variables, right, like this, you have 8, right? So the question is, why is this type of problem? Again, why is this actually, this is like simple example, but if you think about it, like the 0, 1, well, it imitates like flags, basically, or some condition, like, should I go to school today or no? Should I go, some things like you can do or not do, basically, right? So you can use these 0, 1 flags, basically, create this big set of flags which you can explore, right? Unfortunately, if you have like 100 flags, you have 2 to the 100, right? And 2 to the 100 is how much? A lot, right? Yeah, if you check, right, 2 to the 100, let's see here. Let's open up a console. Yeah. Right, we'll do here, right? It's 2 to the 100. Look at this, yeah. So about 1 to the 30th, right? Probably not feasible, no, not feasible at the moment, right? So, again, of course, you have more variables. So even with like these simple variables, right, you can check all possible solutions, right? So even here, it can be beneficial. Unfortunately, I think this is also one of those cases where branch and bound also have struggles, because you are going to be moving, this multi-dimensional space of these 0, 1 flags, right? And you might be end up, it will be hard to cut off the extra. You might end up doing also a lot of comparisons, maybe probably not, but hopefully not exponential, right? So it's exponential. But okay, but let's try to solve. We have like maybe we have some time. We can of course solve it first using brute force, right? Because that's what I would do, right? You go, only 4 variables. Why do I need anything fancy, right? Not only 4 variables. Only have 2 variables. Only 2 possible choices. So 2, 4. Just calculate, right? Remember, when in doubt, use brute force. Even though it's not considered maybe appealing, right? But it works actually, right? Practically it works, right? And then if it doesn't work, you see it's really bad, right? That's when you start saying, okay, you pull out your tools, okay, does greedy approach work? Maybe, can I use divide and conquer? Can I use maybe I need branch and bound, right? So, okay, now, let's see if we can do it on pen and paper, I guess, or we could, of course, since I'm lazy, I would probably do it in a Python, since I really don't want to calculate this, right? So let's open up code space. I think I had code space somewhere here. Backtracking. Oh, there we go. Let's open up code space. Bug-free space. or could we try to do this by hand right now? So, because we have two conditions, right? So we only have one condition, actually, really easy problem, right? So we could solve. Then you have to solve. The thing is, it's harder here. It's like almost. Why do I want to bother? I don't want to bother solving this by, you know, this constraint, right? What would be the optimal solution if we didn't have this constraint? Well, I guess we have our linear programming. We had our linear programmer from last week. I mean, from last lecture, we had it, right? So let's take a look. I think it was here, right? Echo startup, right? Echo startup, we had it, right? I could. So the question is now, do I still have this pulp installed? I think I installed pulp, which was a linear programmer, right? I think I did, right? Yeah, I do have pulp, right? So let's do this linear programmer. Branch bound on bound, and I'm gonna check, right? I'm gonna copy this branch and bound, simple class problem, right? I and B. All right, solving branch and bound problems. Right. So now, of course, I'm going to install it. I need the kernel. What do I have for the kernel? Just environment, right? 312. All right. Let's see if this works. Do I have to install it again? Oh yeah. So it's good. This or no? Yeah. So it's imported. It's very good. So because I installed last time, right? So now let's see. I have to also look at the echo startup. But else? So now I just need to set up the values, right? And let's find the solution. Alright, so I need all of this, right? And I'm just going to copy all of this, right? Oh. And the thing is, it can also do it for you, right? I'm going to say not integer, right? So that's the thing, right? So we could solve also without doing anything, right? Of course, you could use a library here, right? But so I'm going to escape B, right? I'm going to try to now adjust this. So this is what I'm going to copy, right? Solve the following VIP branch and bound, right? On Markdown, sample problem, right? Oh, it worked pretty well. Okay. Well, it has some Unicode which it does not recognize. Let's see if we can solve. Let's see if we can fix it. This is less or equal, right? Yeah, less or equal. It looks like Unicode. I'll just use this, right? Right. Oh no, that's not. That looks like Elvis operator. Okay, and this is less or equal 14, or yeah, yeah. Okay, that looks okay. All right. Now, so we call this. Well, what do we call this? So obviously, so now we can and will solve this using brute force, since there are only two variables with only two possible values each, right? Thus, we have four possible solutions to check, right? Right. Okay. But first we'll do the linear, right? It's like, yeah. We're going to look really easy. So what do we call this? I guess I'll just call it. But we should maybe give us some. What could be these flags? I don't know. I guess we could. I guess we can leave it as BO button solar. I guess, or go to school. And the other one would be to, I don't know. Well, staying in bed is is not related or something else. What else can you do which is not completely exclusive? Or grab breakfast. I mean, that's also yeah. So I guess I'll do that, right? So one will be breakfast, right? Oops. Right. Yeah, we're not going to category, right? So this thing is we need to, of course, know as floats. Yeah. I'll see if they can do the float. I don't know. Yeah, I guess you can. Right. I don't know. right? We have breakfast on school, right? Right, and of course objective function is 8x, okay, 8, 11, right, 8 on 11, all right.
Could you zoom in a little?
Yeah, I'll do me, sorry. Come on, control plus, control plus, control plus. Okay, maybe too much, but there we go. What to do, right? Okay, now, so we have a float, and so what am I doing wrong here with my life? So let's see. That is this one here. This one. What's that part here? Doesn't like this little red thing. So there's some. Oh, comma. Yeah. All right, that's better. Objective function is, and we only have one constraint, right? This one here, 5x, 5, right? x1, 7x2, right? And it's less than what, 14? 14? Yeah, which is silly, of course, right? So we don't need any of this, right? This is all gone. Ah, no, sorry, x1 has to be less than 1, yeah. And x2 has to be less than 1 as well, right? Okay, yeah, those are constraints as well. All right, now print breakfast on school, right? And total profit. School, I don't know, total karma. I guess we'll call it total karma or something. I don't know, right? Optimal life quantities. Okay, right. I don't have, Alexa, don't have inspiration to this morning to do anything more fancier. Okay, so we have float, right? So let's see if this works. Again, I don't know about this category, right? This is a specific, this library specific category. Let's read about this. Continuous. Okay, it's default. Okay, so what I'll do is I'm just gonna get rid of this. Yep, I'm gonna do this. Category is continuous default. Default is continuous, so we don't need specify. Okay. Cat. Yeah. All right. Very good. No. Okay. So let's run it. Total karma. How much karma we get if we could have a non-binary, you know, choices of have a partial breakfast and partial attendance of school, right? So that's what we're trying to do. Let's do it. If this works, I don't know. Welcome. Build. All right. Resolve. Okay. All right. Okay. So breakfast school total karma 1. So it says 1 is the actual value. So that's you know, that gives you 19, right? And this actually works. 5 1 7 1. Yeah, it works. And it gives you 1 1 19. Yeah, of course it works, right? So it seems really too simple. Maybe this problem is really something. If you think about it, yeah, 1 1 is 12, sure. And this is, you know, then you have a maximized 19, right? Simple, right? So we don't really need the branch and bound here, right? It's like we're done, right? We are basically we're done here, basically at the first step, right? But maybe after the break we'll do something a little bit fancier, something a little bit harder, right? So do you see why it works, right?
Yeah.
Yeah. So it took 1 1, right? Of course, you know, here since we are allowed 1 1, right? We plug it in, no problem, right? No, of course, if I made this 10, let's make it 10, right? Then we can't, right? Then it will not work. I'll make it a little bit harder. And then we have a different case, right? Yep. Then it tries to all this solving, all the good stuff. And it says you should have breakfast, but school, no, don't go all the way to school. Or you know, maybe attendance is partial, right? So then you have 15.85, right? So that's more like, so after the break, let's see how that would translate into branch and bound problem. Okay, so that's the solution. That's our upper bound. Basically, I made this, you know, otherwise original constraint 14 would lead to one solution, which is optimal also for integers. All right. Okay, so this is what I will. Let's take a break. Let's continue at 10 o'clock. Yeah, let's continue at 10 o'clock.